Hello. This video will be covering topics such as integration techniques and use substitution and more. It'll be covering sections 5.2 and 5.3. So yeah, let's get started. But before we do, let's go over what actually is integration. Integration is one of the two fundamental concepts in calculus, along with differentiation. While differentiation focuses on finding the rate of change of a function, integration is essentially the reverse process. It allows us to calculate the total area between a curve and the x-axis over a specified interval, which is basically the area under a curve. It also allows us to measure quantities like distance traveled when given a velocity function or total growth over time from a rate of change. It also helps us recover a function from its derivative, so basically reversing differentiation. Mathematically, integration is written as the integral, which is the integral sign, fx dx. Dx represents a small change in x, and the integral sign tells us to sum up all the values of fx across the interval. So the function inside the actual integral is basically the derivative, and the integral is basically we take the integral to find the original function. So there are two types of integration. The first one is definite integration, which basically finds the exact value of the area under the curve within specified bounds a to b. So, and a to b are written across in the integration sign. And the second one is indefinite integration, which finds the general form of the original function without bounds and includes a constant c. So yeah, and also for definite integration, after you take the integral of the function, you have to subtract the original function, so f of b minus f of a, and so f of b is plus c and f of a is minus c, so the constant cancel out, so that's why definite integration does not have a constant at the end, but still include them, because always make sure to include constants so you don't get confused or mess up. So yeah. So first, let's just look at the various integration formulas. Let's start with the most basic one, which is just the integral of a constant dx, which is basically just the constant times x plus c. So in this case, the integral of 2 dx is equal to 2x plus c. And this is why, because if you did take the derivative of 2x, you would just get 2, and plus c would just become 0. So then, and so that's why you would, from constant, you would multiply x to it. So if you did want to, take it back, you could still get the derivative, and this is how it works. And then the next one is just x to the power of r dx, which is basically taking the integration of the power rule. The power rule is basically is used to take the derivative of a function, and this rule is used to integrate the power rule. So basically, x to the power of r dx is equal to x r plus 1 divided by r plus 1 plus c. Always include plus c. R cannot be -1 because in the denominator, if r was -1, then that would be 0, and that would make the function undefined. Let's use this example. The integral of x to the power of 3 is equal to, because right now 3 is equal to r, so it's going to be 3 plus 1 divided by 3 plus 1, which is just x to the power of 4 divided by 4 plus c. Okay, let's do the next one. Integral of e to the power of x dx is just equal to e of e to the power of x plus c. So let's take an example. Integral of e to 2x dx is equal to half e 2x plus c. You may be wondering, why is there a half in front? There's a half in front because if we just took the derivative of e to x, we would get e to x, because the formula of the derivative is just eu times the derivative of u, so that would just be e2x times 2, and that's not the derivative, and so there's no 2 here, right? So that means we need a half to cancel it out and to get the actual derivative. And so when we do these, we actually need to have the reciprocal of what's inside the exponent in the front. And that's how we integrate this function. Okay, let's do the next one. This is the integral of bx dx. And also, like, when we do use substitution later in this video, it will be easier for you to actually integrate this and not overcomplicate stuff if it's hard for you right now. And so yeah, the integral of b to x power of x dx is equal to b power of x divided by ln b plus c. B has to be more than 0 because obviously you can't, take a negative exponent or take a power of the negative exponent. Not possible. And b has to be, it cannot be 1 because ln of 1 is 0, and that will make the function undefined. So for example, if we took integral of 3x dx, then it would just be 3x divided by ln 3 plus c. Pretty simple. Let's do the next one. The integral of 1 over x dx is equal to ln absolute value of x plus c. Again, you can always just go back to check take derivative of this to check the derivative of this to check your work. And this is another example, the integral of 1 over 3x dx. You bring the 1/3 over in front of the integral, and you have 1 over x dx, and then if you integrate it, you just get 1/3 ln absolute value of x plus c. Never forget the plus c. Okay, now let's just go over these. More trick stuff. Okay, so the integral of cosine x dx is equal to sine x plus c because the derivative of sine is cosine. And then integral of sine x dx is equal to negative cosine x plus c. If you're like, why is it negative? Well, the derivative of cosine x is negative sine x, but we have positive sine x. That means that cosine needs to be negative so we can get a positive. And remember the plus c. Integral of sine squared x dx is equal to tangent x plus c. The integral of cosecant squared x dx is equal to negative cotangent x plus c. Same thing as this. It's negative because we want to get a positive cosecant, and we know that means it has to be, cotangent has to be negative. And then integral of secant x tan x dx is equal to secant x plus c, and the next one is integral of cosecant x cotangent x dx is equal to negative cosecant x plus c, and we need this to be negative so we can get a positive cosecant x cotangent x dx. Okay, and now let's look over the inverse trig formulas. So the integral of du a squared plus u squared is equal to 1 over a inverse tangent u over a plus c. So yeah, these are just this is just the derivative. This is the derivative of inverse tangent, and this is just the original function, or to take the integral of to get the original function. And this is integral du over square root of a squared minus u squared is equal to inverse sine u over a plus c, and integral of du divided by u times square root of u squared minus a squared is equal to 1 over a secant inverse secant absolute value u over a plus c. Just remember that just like differences between these and how like inverse sine is negative u squared, and for inverse secant it's negative a squared, and they both have radicals in the denominator, while inverse tangent does not, and it's positive. And yeah, memorize these formulas. Like for example, here we can see that the integral of 1 over 9 minus x squared is with u squared is equal to x squared, and then so u is equal to x, and then a squared is equal to a is equal to 3, and so then it would just be inverse sine x divided by 3 plus c. It's going to be more easier when we use substitution, so when we actually go through it, we're going to know more how to do these types of questions. But just now you get the basic gist of what the formulas are, and be sure to memorize them for future use, so your life will be easier when you get into use substitution, because it'll be slowly getting harder and harder. Okay, now before we go to use substitution, let's just cover of like how do we integrate absolute values. So basically okay, when we integrate absolute values, we basically separate them from positive and then negative. So here we can see that x is negative from let me just rewrite this again, as if it's unclear to see. From x is negative from negative infinity to 0, and positive from 0 to positive infinity. And so yeah, so first we find when x is equal to 0, and then we have to find out when the function is positive and when it's negative, and that's when we split them up. So here, when it's negative, it goes from the interval is going from negative infinity to 0, and then you have to add that from 0 to positive infinity. And yeah, so here I took the integral of this function to get negative x squared 2, and then for this one function I get x squared divided by 2, and if I had given values, I would just have to plug in both values and subtract 0 to negative infinity, and positive infinity minus 0. And if you plug these in, if you're given values. So yeah, that's how you would do absolute value questions. Yeah. Now let's move to substitution. Okay, so what is use substitution? Use substitution is an integration technique that simplifies integrals by substituting part of the integrand, which is the expression being integrated, with a new variable u. It is a reverse of the chain rule used in differentiation. Now, when is use substitution useful? And what are the several factors to consider when selecting an appropriate u? Okay, let's start with number 1, composite functions. When the integral or integrand has a function inside another function, for example, with sine x squared or e to the power of x cubed, we can see this is a function inside of another function, where u in this case would be x squared, and u in this case would be x to the power of 3. Now, continuing on to that, an example would be the integral of x cosine x squared dx. We can see that the term x squared is inside the function of the cosine function, suggesting that u is equal to x squared. And now we can see it's also useful for matching derivatives. When the derivative of part of the integrand appears elsewhere in the integral. So an example is derivative of x e to the power of x squared dx. The derivative of x squared is 2x, which matches the term x in the integral. And this could be used to simplify the function to get the integral easier. Number 3 is simplifying complex expressions. So similar to matching derivatives, we can also, simplify complex expressions. When substitution transforms the integral into a standard or easier to solve form with powers, exponents, or trigonometric functions. An example of this would be the integral of x over x squared plus 1. Letting u equal x squared plus 1 reduces the denominator to a simpler form. So just, simplifying the expressions as u equals x squared plus 1. We can say the derivative of this would be 2x. We can replace the du and, make the equation more simpler. The function more simpler. Okay, number 4, recognizing patterns for inverse trigonometric functions. So when the integrand matches forms like 1 over square root of a squared minus x squared, and 1 over a squared plus x squared, or 1 over x times the square root of x squared minus a squared. Now, as I said before, if you noticed that from when I said about the memorized equations, you can notice that these are all the derivatives of inverse sine, inverse tangent, and inverse secant. And so in this case, use substitution helps to align the integral with the standard formulas for the inverse trigonometric functions. For example, let's take the integral of 1 over 9 minus x squared dx. So here we can see that u squared equals x squared. And so then u equals x, and then du equals dx, and then a squared equals 9, and a equals 3. And when we look at this function, we can look with this equation that this is going to be inverse sine, and then we put, which matches to inverse sine x by 3 plus c. So if you know your equations, it makes it much easier, and use substitution helps you just to make the process easier for you and to keep track of the terms. And also it helps that, like, in cases that, like, even though the format of this might look similar, it necessarily does not mean it's going to be an inverse trigonometric function, and using u substitution, we can figure that out, and it will lead to less confusion. And also, like, just to know, like, how you know which function is which for the inverse trigonometric function, you just have to look for, like, the formulas. So we know that if there's a negative before the actual x value, like x squared, we know that's that's inverse sine. And if it's both positive and there is no square root in the denominator, we know that's inverse tangent. And when its denominator is square root with negative a squared and x in the front, we know that's going to be a inverse secant function. So there's multiple ways to check it, and you should be very careful when we're doing this and not just assume something, but we should also, like, substitute and, take the derivative to check if we were actually doing everything right. In this case, use substitution is very helpful for that. So, and then we have number 5, radicals. When the integrand involves square roots, fractional exponents, or nested radicals, use substitution simplifies the radical by substituting the expression under the root as u. So an example of this would be integral of x over square root of x squared plus 4 dx. So let u equal x squared plus 4. The du would be 2x dx, and we could just put that, put du into the function to simplify this function more. And then we have the next one, which is the integral of x squared, x power of 3 plus 1 to power of 1/3 dx. This is kind of like function inside of another function, but also like a radical. So then let u equal x to the power of 3 plus 1, and then du would be 3x squared dx, and we could use that to put du into the function and simplify this further. The next one is the trigonometric powers. When integrals involve powers of trigonometric functions like sine squared x, cosine squared x, or products like sine x, cosine x, use substitution uses trigonometric identities and substitution to reduce the powers. Okay, so let's look at this example here. The integral of sine squared x cosine x dx. So we can see that we can let u equal sine x, and and why would you do that? Because we know that the derivative of sine x is cosine x, right? And so we do this because then we can replace cosine x by du, and then sine square x with u square x, and we can take the integral easier. So this is like one of the examples where you have to think about it, like to match, if they have matching derivatives, or if we can simplify like expressions easily. So we have to think like, oh, what can I replace with u to make this function like more simpler, right? And this is how we do this. And then we can simplify it and then take the integral of u squared x, and then then replace it, substitute back with u. Now let's start doing more examples and talk, and I'll explain even more concepts of how the other various types of u substitutions. Okay, so let's start. I want to start off with how it's important to also consider the denominator first. So let me just make a note of that. If you notice a pattern while we're doing problems is that for some functions, considering the denominator will let you identify what the u is. Especially when dealing with rational functions. Right? The denominator often suggests the best candidate for you. And this is especially useful when the denominator is a polynomial or has powers / roots. And the numerator is related to the derivative of the denominator. Now let's look at this. Let's do this example. X over x squared plus 1 dx. Okay? So the denominator is x squared plus 1. And this is a rational function. And so this suggests that u equals x squared plus 1. And so, now let's check that. Let's take the derivative of this. Du equals 2x, right? And this matches, don't forget the x. This matches the numerator. So this works out. We just have to make sure to replace like this so we can plug it in, make sure to scale by a constant, and then we can replace a function. So then we can say that half is equal to 1 over u du, which then we take the integral of, because we know that I over u by the formulas that we talked about is a memorized formula, and that would be half ln u plus c. Never forget the plus c. That's it. So basically, the denominator provides a structure that aligns well with substitution, turning the fraction into a simple integral. Now let's just do one more. We can see from here that, x squared over x to the power of 4 plus 2 squared dx. Okay, so we can see that when the numerator and denominator have polynomial terms, check if the numerator's degree matches the derivative of the denominator. So let's do that. So our denominator, is x fourth plus 2. And since this is like we're going to take the inside function of this in the denominator. So this would be our u. And let's say the derivative of this. What is the derivative of this? Which that would just be 4x to the power of 3 dx equals du. Sorry, the top should be x to the power of 3, not 2. So that one. And then we can see that this will match the denominator if we just this. So now we can replace this function, x to the power of 3, with 1/4 du. So it will look like this. Which will just become don't forget your du's. And then also, now let's just take the integral of this function, which just would end up as, and make sure to substitute back in your u's. So it would just be 4 So matching powers between the numerator and the derivative of the denominator allows substitution to reduce the degree of complexity. Okay. So yeah. And this is basically similar to radicals and roots, as if this was a radical, we would just take, again, the inside function and do the similar, basically the same thing as we did before. So the same concepts. Okay, let's do one where we have to simplify trigonometric identities before substituting. Now, if you remember your trig identities, let's write some of them out. I know that sine squared x plus cosine squared x is equal to 1. I know that tangent squared x plus 1 is equal to secant squared x, and I know that cotangent squared x plus 1 is equal to cosecant squared x. These are some of our trig identities that are really helpful in this scenario. So let's do one of them. Let's do an example. Okay, so example we could do would be the integral of cosine power of 3x dx. Okay, so this can also be written as cosine x cosine squared x dx. And I know that sine, we're using this one, that sine squared x plus cosine squared x is equal to 1. So then cosine squared x is equal to 1 minus sine squared x. Okay? So, and then we could replace cosine squared x with this, with our trig identity. Now we would have to distribute it. So we can simplify it even further. Okay, I'm gonna personally, you can, if you didn't know it already, you can take the integral in separate integrals as well. We can separate the terms. So I'm gonna separate this into the integral of cosine x dx minus the integral of sine squared x cosine x dx. Okay, I know that in this function that u can be sine x and y. Okay, let's think about this. Why should u be sine x? Because if u is sine x, then the derivative of sine x would be cosine x, and then we can use that to replace cosine to du and sine to u squared x to simplify the function further. And and you might be thinking, why can't it be cosine x? Well, then it would just be, cosine x would just be sine x. And that would just make it more complicated, as sine is squared x, sine squared x and cosine x, and that would just, you know, it would still not get rid of all the signs, and you know, it would overcomplicate it. So just have to think about it for a second before we do get into it. So then yeah, then this would become du equals cosine x dx, and now we can replace the function u squared, and this would just be du. Now let's take the integrals of both. So the integral of cosine x, as we talked about the formulas earlier, the memorized formulas, I know that that sine x gives me cosine x, so it would just be sine x. And I know that this would become u3 over 3 by our formula. And then we have to substitute back in our u, so it would become sine x minus 1/3 sine or 3 x. I'm just gonna put 1 in. Oh, that's not required. Don't do that. You don't have to. I mean, you could. I'm sorry. Anyways, plus c. To me that kind of looks awkward, so I'm just gonna rewrite it again. Nice, that's the answer. So yeah, it took a little bit of meddling, but just know that if you are stuck, you might need to use one of your trig identities. So make sure to review those a little bit more. Okay, and now let's look at another type. That's interesting. Okay. So let's say the integral. Sorry, I can't really see that. The integral of 1 over x ln x dx. Okay. Now, first let's just look at this, okay? We are gonna let's focus on the denominator, because we can see that this is a nested function, okay? And so I'm just gonna write that down. This is another type, and this is like one of the nested structures one, and you sometime, and this one, so like these types of problems, when there are like multiple layers of function that exist, like with like in this, like, you know, square root of ln x, you know, substitution works best by addressing the innermost function first. So like what's inside of the function, like what I've like been saying from the beginning. So we can see that the innermost function is ln x, right? Because we have to look in the nested function. The nested structure is square root of ln x. And we can see the innermost of it is u equals ln x, right? Now, let's take the derivative of this, which gives us 1 over x dx. Now, we can see that du replaces 1 over x here. And I've been saying this from earlier, it's important to look at your denominator first to see what you can replace u with. And so we can replace our function, or replace parts of our functions. With like matching derivatives. So yeah, it's important. Now let's just put this back in. And so it would just be 1 over square root of u, and then du, which replaces 1 over x. See? Now it becomes more simpler than what we had before. Now we can just take the integral of this. So this would just be 1/2 du, and the integral of this would just be 2u½ plus c, don't forget your c. And then what do? You have to substitute back in your u, and I know my u is ln x, so it just will be square root of ln x plus c, and that is our answer. So yeah, that's pretty simple. Now let's look at another problem, and this one is a little bit of a different approach than before. Okay, though it kind of looks similar to this one a little bit. Let me just show you. But it's not really the same process as well, kind of. Okay, we can see that this is kind of similar with having like the x variables, you know, in twice, like kind of similar to this. And we can see that this is also like an inside function, right? But this is a little different. Okay, first let's start by doing what we know, and we know that we should say that u is equal to our inside function, which is 4 minus x. And now let's say the derivative of this would just be negative 1 dx. And we can replace, we can just put that in our integral right now and just say that negative 1 is x 4 minus x du. Or, sorry, this should be u. Let me just rewrite that again. Again, try not to make silly mistakes like this, but it's fine. Anyways, so yeah, that's what we have now. And then what we're gonna do, I mean, we can't take the integral of this, right? This is not further simplified. Like, what can we do, like, to make this better? Like, because this still looks bad, right? What we can do is, since we have two x's, we have to make the entire function with u, because that's the only way. We can't have one x and one u. That won't make any sense. So let's just do this. So we can say that x equals 4 minus u, and we can put that in our function and say 4 minus u is u and du, like that. And then we can say that 4 minus u and then square root of u is basically u 1/2, and yeah, and now let's distribute this, which is gonna be 4u 1/2 minus u, and that's one with 1, so that'll just be 1, 2 du. Now let's take the integral of this function. The integral of this function would then become it would just become that and plus c. Because we're just adding 1, we're just flipping that reciprocal, so same thing with here, and that's what we get for integral. And let's simplify this further with negative 4 2/3 u, that. We're just flipping this over and bringing it up and just, you know, keeping it like that and spreading out to the negative 1 front, and this will just become positive because negative is positive, and so bringing out the reciprocal in front, flipping it up, and then just like, yep, that. And now we can further simplify this by spreading out, distributing the fractions and putting back in our u. So then it would end up just being 2/5 4 minus x 5 over 2, or to the power of 5 over 2, and then x, and then okay, and that's it. Now don't forget your plus c's. So yeah, this is another kind of problem we have to do, and you know, just know that like if it's like this, and you have two different variables, you're most likely going to have to find what x is from u, like this. So yeah, just another way to do stuff. Let's do a couple more different problems. Okay. I'm gonna write out actually. So let's just do one problem here and then I'm gonna write it later because I don't waste paper. Okay. Let's do one with e in it. You can see that. Okay. This one is not as hard, but just kind of, you know, a little different vibe to it. So this is a function. I'm just gonna write it out real quick. Okay. Okay. Now, we can see that there's an inside function here. There's an inside function with e to the power of y4 power minus 7y squared. And so obviously I'm just going to take that. Whenever in doubt, just take the exponent of e. That's, you know, most likely going to be your u always. So, and most likely should work. Anyways, then, so our derivative would just become 4y e minus 14y. And let's just factor this real quick. And I'm just going to take -2 out to get, because I want to get my numerator, right? So I can replace that by du. That's the aim, right? Since, yeah, don't forget your dy. Remember, it has to be the variable, so it can't be dx if it's y, you know? Just remember that small stuff like that will, you know, throw you off. Then we can see that 1/2 du equals y minus dy. And then we can put that back into our equation, which is just going to be half eu du equals, which just equals like half eu plus c, right? And now, because we took the integral of that, and if you're wondering how I did this, just like, you know, remember the memorized formula sheet is that the integral of eu is just going to be eu. So, and then you put your half back here. And then don't forget to substitute back in our u, which will just be and that's it, guys. Okay, and I also want to do also a little different kind of vibe. Oh. Okay, guys, let's do a quick one. This one is just, I talked about this before, but didn't explain it with substitution. So let's just kind of do that real quick. Okay, so we can just do the integral of, let's just do, it's just a quick one. So I'm just gonna do like 3x. Okay, so since, you know, this is our inside function, right? U equals 3x. And then du equals 3 dx. And so then we have to say that 1 du equals dx, right? And then we can put this back in to our equation, which is 1/3 e3x. And we know that the integration of the formula is just going to be because by the formulas, our integration will just be e3x, and then 1/3 of that. That is our answer. Ooh, and don't forget your plus c. Never forget your plus c. So yeah, this is more of a simpler way to find it instead of confusing yourself, thinking too much about it. Like the way I explained it in the beginning of the video, this is just a more simpler way to do it, so you're not, you know, thinking too much of what you're doing. And it's really easy because you're just looking at your inside function like normal. Okay, let's do more. Okay, this is example number 8. Let's do, okay, I'm gonna write out, there's 3 parts to this, which is interesting, and they look very similar, and I just wanted to talk to you about how you would end up doing this, right? Oh, sorry, don't forget your integration sign. That's just a random function then. We don't want that. Oh, over dx. Guys, I'm glitching. Don't forget that, or you don't know that you're going back to, that's the derivative and you're going back to it, right? Okay, there we go. And then we have c, which is, again, they're very similar, but that's what I wanted to show you how you would go about doing these, right? Okay. Okay, let's just, you know. Okay, first let's start with a. About now, you should know that we're gonna look at our denominator first. I can see that, like, let's just try it, right? I feel like we could make our u 1 plus 9x squared. And then our du would be 18x, right? And then we have 3x on the top, right? So that tells us that we need to, you know, get rid of a constant in front. So I'm just going to say that 1/6 du is equal to 3x du. And now we can replace it. So then, oh, sorry, this is dx, not du. Don't do that. Okay, so then we can just replace it by 1/6 1 over u du. And we can see that the integral of this function by our memorized formulas is that the integral of 1 over u is just going to be ln u, absolute value of u, plus c. And don't forget to bring the 1/6 front, and don't forget to add in plus c. And also we have to put back our u, substitute back in our u, so it's just going to end up being, say it's ln 1 plus 9x squared plus c. Okay. And this is what I wanted to show you. You can recognize that this could also, in fact, be our tangent, or inverse tangent equation. And I was talking about earlier how just because it looks like that does not mean it is inverse tangent. So us using u substitution, we can see the different ways we can integrate stuff, and that necessarily does not have to be something like, and we can always check our work, and that using u substitution, we can just it's gonna make our life easier to know what we're doing, right? Like this, the tangent, it looks very similar to this du over a squared plus u squared here, but it's not. And just us using u substitution, we can figure out why. Yeah. And if you wanted to know why it's because there is a 3x in the numerator, and in that scenario you can't really get rid of the x, and it doesn't really follow by the rules of inverse tangent, since it has to be du over square root, or du, not square root, du over a squared plus u squared, and that doesn't follow that rule. So you can either do that or just use substitution to really know what you're doing. Yeah, just know what you're doing. I don't know. Anyway, let's do b. Okay. I know that b I can see that in the denominator there's an inside function. So I'm still gonna make my u 1 plus 9x, and I'm gonna take the derivative of this, and again x squared. Derivative of this would just be 18x dx, and then I would do the same thing and say that 1 over 6 du equals 3x dx, so I can replace it by du, replace 3x by du, and that would just be equivalent to 1/6, 1/4 du. But this function is different because in this case, we can see that it can't be ln because it's not 1 over u, it's 1 over u to the 4th power. So now we just have to do regular substitution with just 1 over 6 is basically 1 over du, and then let's just substitute this. This would just be equal to 1 over 18 u negative 3 plus c, and substitute back in our u, and it would just end up being okay, that is our answer. Cool. And now let's do C. Cool. I know that C is from seeing this, I know it's going to be inverse tangent because it's just 3 on top, right? As we talked about before. And I know that, and let's just do this. So you can say that u squared is equal to, let's just say that u squared is equal to 9x squared. So I know that u is 3x. And I know that a squared is just 1 and a is 1. So from just that, I can pinpoint of what it would be. Ooh, and then I can just say the du would just be 3dx. So then what would end up being is that because I know the equation for inverse tangent, or sorry, the integral of inverse tangent, which is going to be just 1 over plus c. So from this, I can say that this is going to be just 1 over 1 and 10x, and I know that u is going to be 3x, right, over 1 plus c, so it's just like plus c, and that's just how easy it was. And yeah, that's pretty much it. Okay. Oh, and also if I didn't pinpoint earlier, the du equals 3dx replaces the 3 on top. So yeah, so that's that. So then that's, so it becomes, instead of like 3 over 1 plus 9x squared dx, it just becomes 1 plus u squared dx, or du, and then you would then take then you would just go back to this. So yeah, so if you didn't understand what happened to the 3 here, well then just was replaced by du, and then we took the derivative, so, or sorry, not derivative, the integral. Yeah, that's it. I don't know, we can okay, let's do a few more, and I think then we'll be good and you can understand like how to do all of these properly. Okay, let's do secant 1 minus c tangent 1 minus c dc. In this case, I'm just going to take the inside function of both, and this happens to be the same, so we would just take the inside function of u equals 1 minus c, and that would just be, the derivative would just be minus c, and then we would just have to just put it up front like here, so it would just be like secant u tangent u du. And you can think about this before, but this should work. Essentially, if you just thought about if you replace this secant u tangent u and thought about what would the integral be of it, we can see it's obviously going to be secant. So secant u, so the integral of this in paradise would just be secant u plus c. This one is pretty easy. Just have to be familiar with your formulas and know that you can replace inside functions with them. And yeah, that's it, guys. And let's do a little complicated looking one. It's not that bad actually, but yeah, let's do this one real quick. Cosine 2x yeah. Oh, and this, only this is outside the function, the dx, so dx is outside the function. Just really weird. Okay, this looks like a really, like a long function. It's kind of looking scary at the moment. So you might be thinking, oh, like, oh, this is the inside function 2x, we can just replace that you know. But then what you're not thinking about is that, like, if you do take it, if you say, oh, u equals 2x, then it's just gonna be, what the derivative is gonna be 2, and it's not gonna do anything. And we can't take, but the biggest thing here that's that I'm looking at is the radical, right? There's a lot in the radical, and it's hard to get rid of that without actually taking the u of that, right? So for me, I'm gonna take the u of that first because that's the most opposing thing right now. It's get rid of that and find out, like, you have to simplify this first, right? So I'm just gonna say u equals cosine squared 2x plus 5. So then it's like the derivative of this, which is gonna be I know that the derivative would just be -4 cosine 2x sine 2x dx. And then from here, we're basically gonna do that. basically, we can say that right? So yeah. I just multiplied it by 5 over 5 and 2 just to get the so I can get the function so I can replace this by du. This looks a little complicated, but like, let's just continue. And then basically let's just replace this by u half du. So putting u into this and we replace this by du. And then we just get, this is a 3. And then we're gonna put back our u in. So cosine 2x plus 5 3 over 2 plus c, and that is our answer. Yeah. And yeah. I just got this because I wanted to make sure all the x's are replaced with u's so we can compute the differential. So I computed the differential so we can eliminate all the dx's as well as the remaining x's in the integrand. So yeah. And then you have to just like just kind of like rewrite it to get this and get the answer. Yeah. See if there's more to do. I feel like there's not really that many left over as we just did so many of them. Ooh, I have a good one here. Let's integrate. We didn't really do one of these yet. This one is a little trickier. Yeah, we're almost done. Let's just do a couple more problems and just end it. And I'll just end. You should be able to know how to do them, I guess. Integrate x 3x squared plus 1 dx. I should already remind you of one of the formulas. Okay. And if you knew already, we should always be looking at the exponent or the inside function and recognize it. So it should be x squared plus 1 to the derivative of this will just be 2x dx. And then let's just take half du equals x dx and then replace this function with du and u. So it'll just be like this. And oh, and don't forget the half. And then make sure to, let's say the derivative of this function. So if you look at the formulas from before, you can see that this function, and so let's use that formula to take the derivative, or sorry, the integrate it. Okay, so it'll just be 1/2 3u to ln of b. So the function was bu to ln of b, so that just the b would be 3 here in this case. And that would, with plus c, obviously. It's gonna distribute that further and just to ln 3 plus c, and I replace u with so let's do it back in, and I know that ln 3 squared can be written differently, and that could just be, because we can, and I know this can be written as ln 3 squared, and so bring this back like that, and that'll just be 9. Oh, and then let's like make this a little like that. It's like smaller. Yeah. So yeah, that's it, guys. Yeah. Pretty simple. If you memorize the formulas, it should not be difficult. Okay. Let's do so the last few ones. Let's do definite integrals. Or yeah, these are fun. This should be interesting. Pi 0 x sine dx. So basically, this is 0 to pi, by the way, sorry it's a little messy. So obviously this is the inside function, so we'll just say that x squared is equal to u. So then du would just be 2x dx, and then half du equals x dx. Okay. Anyways, we can just say that it's half and and we can also adjust the integral, the interval. So let's just plug it into x squared, right? So squared is equal to u, so that must be pi is equal to u. You know, that's the same thing with 0, but that's just gonna be 0 because u, so it'll just be 0 to pi instead. And then we're gonna replace, since du replaces, half du replaces x, that'll just be that. That'll be gone, and then it'll just be sine u du. Then let's just take the integral of this, which will just be cosine u from 0 to pi. Then we're just gonna have to plug that in. It's gonna be negative half cosine pi minus cosine 0. I know that cosine pi of it is just -1. I know that cosine 0 is just 1. So it'll just be half and it'll just be -2, and that'll just be, or 1. Okay. Wait, yeah, cosine pi is just 1, -1. Wait, actually, sorry, that would just be negative 5 over 2, right? Because it's just half times plus 4 over 2. So, yep, that should be correct. This is not exactly U substitution, but let's just do a long division integration problem. Oh, never mind. I might be going, sorry, this is right. I was right, it's actually just 1. Sorry, I got confused and added them up instead. I was right, guys, I was right before. It is positive 1, not negative 1, it's positive 1. I was right in the beginning. Anyways, that's why you check your work, guys. but yeah, just a little tired. Let's do a long division problem and then maybe do one more and we'll call it a day. But yeah, like, did a lot of problems that involved things, so good. Okay, so let's do a couple more. To long division one. This is not U substitution, but this is just a long division one. So yeah, let's do that real quick. This is pretty easy one as well. But yeah, if you have a term like this, and you can't really exactly just differentiate it, and you can't really use a U substitution at all because there's no inside function or anything like that. So let's, do regular oh, sorry guys, that's not how you do it. You differentiate, you do the inside you. Okay, now let's do it. I know that that negative half equals negative 1, or sorry, positive, and then you put negative and that cancels out. This becomes positive, so that just becomes negative 4, and you can't really put anything else on there, so it just becomes negative half minus 4 over negative 2 plus 2. And that we're taking derivative of, or integration of, and we factor this out, and this becomes we can do negative it becomes positive 2x minus 1, this becomes 2, and this becomes just like plus 1 dx, and let's just integrate this real quick. We can integrate this by separate terms, so this is going to be plus 2 over x minus x dx. Oh, can't see that, can you? I don't know. Just separate this work. So that just becomes, this becomes x, and this becomes just oh, and we get that because, again, we look at the denominator, and so from here I just said u equals x minus 1, and so then du equals just 1 dx, and so they can do 1 over u, so it'll just be dx, and we know that derivative of 1 over u by the memorized formulas is just going to be 2 ln absolute value of u plus c, and I know that and let's substitute back in u, so that's going to be just that, and that is it with this question. Why don't we just do another one that's okay. Let's do just one more and call it a day. Let's do, I'm not quite sure. Which one should I do? We can do okay. So yeah, let's do this one. From pi, square root of pi over c0, 5x, cosine x, cosine 3. Yeah, it's kind of similar to the one we did before. But we'll be using two methods. One is using just x boundaries and the other one is using u boundaries. So first let's do the one using just x boundaries. So let's make u equals x squared because that's the inside function. And then so du would just have to be 2x dx. And so x dx would just be du over 2. Since we have 2, let's replace x. So it just have to be 5 square root of pi 0 cosine u times du over 2. I'll also just do this. Then it would just be cosine u du. I know the integral of cosine is just gonna be sine, so, and I know that we should substitute back in our u's. And I know that at x equals square root of pi, u is equal to pi squared, which is pi, and then at 0, x equals 0 and u equals 0 squared, which is just 0. So then it'll just be sine pi minus sine 0, and that's gonna be, so yeah, using just, you know, the sine pi 0 and sine 0 equals 0, so that's just gonna be 0. And now let's using u boundaries. First let's convert x boundaries to u boundaries. That's just when x equals 0 and u equals 0 squared equals 0, and when x equals square root of pi, u equals square root of pi squared equals pi. And so let's rewrite the integral from 0 to pi, just rewrite it as 5 seconds 0 to pi cosine u du, and then let's solve the integral from cosine 0 to pi. 5 seconds sine pi minus sine 0 equals 0. So yeah, you know that both answers are the same, or we can see that from both x and u boundaries we still get the same answer. So yeah, and I think that's pretty much it. We had a lot of questions here, but this is all the work. Anyways, now we know and yeah, that's it. I just want to, now we know like how u substitution is really useful in terms of just, you know, and then last but not least, let's try to use u substitution to integrate tangent and cotangent. Okay, let's do this. So I know tangent is equal to sine x. Can you see that? Sine x over cosine x. Right, and so I know that we're going to take the if you want to integrate it, just have to integrate cosine, or sorry, sine over cosine dx, right? And I would let's make u equal to cosine. So then du would just be negative sine x dx, and then so then I would just get negative 1 over u du. And I know that the integral of 1 over u is ln u, absolute value of u plus c. And I know that to plug back in or substitute back in my u. And so yeah, I would end up getting ln cosine x plus c. Which is also equivalent to ln secant, absolute value of secant plus c as well. And now I'm also going to integrate cotangent. I know that cotangent is just going to be cosine over sine, and I know that cotangent dx is equal to cos x, or the integral of cotangent x dx is equal to cosine x, integral cosine x over sine x dx. I'm going to make my u equal to sine x, du equals cosine x, and then, or cosine x dx, and then, so then my integral would just be 1 over u du. And I know that the integral of 1 over u is just going to be ln absolute value of u plus c. Substitute back in my u, just get ln absolute value of sine x plus c, or yeah. So yeah, this one works. And I just used, and if you're wondering why I was using u as cosine x and for cotangent sine x, I just usually I stuck to my u's as the denominators, because if you're not sure, you'd just rather use a denominator, and so that works. And also the denominators also gave me the derivatives to replace my numerators, and so yeah, this avoids, so without actually using any memorizing another integration formula, you can just easily just integrate tangent and cotangent. And so yeah, this is how you would do them. And just stick to your rules and just look at your new denominator and see if you can replace your numerator, values in your numerator. So yeah, that's how you do it. Yeah. I think that's it. I'm gonna end the video. I went over multiple forms of u integration, or yes, u substitution, not integration. Oh yeah. And then just on topic of integration as a whole. So yeah. Thank you.